who work at the Hive. So you can see Ravi, Pashu, Lance, Aaron, right, and a bunch of others who have cut off. But on the left-hand side, you see location, relationship, first degree, second degree, and so on, and current company. So there's a current company which shows you people who work in other companies. But the general idea is that you get a UI which is different from typing text in a search box, through which you can drill down, see some counts, see some attributes of the search results that are shown to you. Right? In those days when we were building facets, Lucene did not support facets. Today, Lucene has capability to support facets. So what we had to do was we had to build our own faceting system on top of Lucene, and that's called Bogo. Again, system that is, you can see details of it online, so I won't describe it in detail here. The general idea here is that Bogo is a layer on top of Lucene that before you start searching on the index, it goes and fetches important parts of the index, inverts it in some way, creates an in-memory store through which it can very quickly go through facets, count them, and display them the way you saw it on the previous slide. Finally, type ahead. Type ahead or instant search is search as you type. So as you type characters, you get a drop-down box and the results keep showing up. And as you type, every character you type creates a different set of results. So conventional wisdom, unfortunately, is that you cannot use a Lucene-like system to support type ahead. You see that in university courses, and you see that in textbooks, and companies have made that assumption and therefore built totally different systems to support type ahead. We did that too. Facebook did that. LinkedIn has done that. So LinkedIn built a couple of systems, Clio, which is the type ahead search engine, and Prati, which is a content store that it uses to store data. And jointly, it supports a type ahead experience. Subsequently, we got rid of that conventional wisdom, which is wrong, and we moved type ahead into a Lucene-like system. So you can see that we've built a whole bunch of systems to support search in many different ways. And this was the state of the LinkedIn search framework when I joined the company, and everything was working really well. The only problem was that a good problem to have was that we were just growing and growing and growing. The number of members increased, the number of data increased. The kind of search we had to provide was getting more sophisticated, and obviously we started having scaling problems, right? So around the time I joined, everybody in the team was talking about how do we scale it, how do we keep things alive, how do we keep things from crashing. The usual problems that all of you, I'm sure, have had or still have all the time, right? So now I'm going to talk about everything that we've done since the last year and where we're at right now. So keep in mind that I'm talking about a journey that we've gone through at LinkedIn. Starting from the very beginning, we picked up Lucene and built a whole bunch of stuff, and we kept scaling. Some of you might be more ahead of us in the journey. Some of you are earlier at this stage, and I hope you can pick up some of our experiences and adapt that to your needs. So now you probably have guessed a few of the growing pains that we have encountered with the stack the way that I just described. So one of the big problems that we have is rebuilding the index from scratch is extremely difficult, right? Lucene gives you the capability of adding documents one by one. We have a content store that we have to update, again, document by document. So the whole framework makes it very difficult for us to rebuild the text. What if we have a bug that for a particular kind of update causes the index to get totally corrupted, and all our copies of the index get corrupted? We had to now then start from scratch and rebuild everything. Major pain. The other related problem to this is if we want to make some changes to the index, suppose we come up with a cool relevance improvement for which we need to add a bunch of stuff to the index. That also requires us to rebuild the index for every single document because we can't incrementally update every piece one by one. So again, major pain. Since the index is being updated live on indices that are serving real traffic, we don't have a lot of compute power that we can use when we update the index. The kind of compute power that you guys are used to when you build map reduces, for example. So we can't do fancy relevance algorithms offline or during the live update process and make that index really rich. So our index has to be pretty bland, and we have to do all our compute intensive activity during the search, during the actual search process. It's again not something that scales very well. And as I've told you, the live updates are at a document granularity. So in fact, what we do is, even though we have that search content store where the live updates are at field, the Lucene index still has to be updated at a document granularity. And as our corpus size, the number of members keeps growing, the complexity of the search keeps growing, the number of posting lists that hit a document keep growing, that kind of live update cannot continue to work. We have to do something to do it more incrementally. Scoring. So as I said, Lucene does some default scoring, and then Sensei allows you to add something on top of it. That is inflexible. Typically, what we want to do with scoring is we want to define a bunch of features, we want to engineer a bunch of features, and we want to send it to a machine learning algorithm with training data, come out with a formula that becomes a scorer, and be able to iterate on that. And these things can get pretty complex. The way Lucene plus Sensei provides the infrastructure for scoring doesn't make it very easy for us to iterate, or you perform this kind of this kind of a scoring system. Okay, so then other problems with respect to just infrastructure, the way things got built was we built too many open source components. We had a Bogo, we had a Zoe, we had this, that, and all of them were put together into a search engine. But then each of these open source components were the baby of one particular engineer. Eventually everybody left the company. They went to different places and they continued to maintain, and we were left with a whole bunch of pieces, moving parts that we had to keep together and keep together connected. That also caused trouble. And finally, as we started scaling, as I said, we built a search engine, but that search stack was flexible enough to be used for other purposes, as I mentioned, for recommendations, for newsfeed, for ads, and so on. And each of these systems also started having growing pains, scaling problems, and each of these systems also started having to move away from the stack and make some tweaks here and there. So we started diverging. That was a big problem too. And as we started diverging, again, maintaining many more stacks. So these were all the kinds of problems that we started seeing, just because we had a good problem that we were scaling, and the company was growing, and our data was growing, and we needed to build more complex search use cases. Okay, so what we did was we took a break last year around this time. We figured out that we need to build something new. We need to build a new stack that can take us to the next level of scale. And the last year was a pretty phenomenal year. We all worked together as a big team, and maybe a small team, more than 40 people, and built this new search stack. We've got 2 verticals in production already, member type ahead and company type ahead. So running very well, running successfully, no problems. We still have a lot of work to do to migrate a lot of our other search verticals to the new framework. I'm going to spend a little bit of time now describing some details of this new framework that would be interesting to you without getting into too many gory details. So, very standard architecture. You get a user query that comes in, it goes through something called a query rewriter that converts the query into a structured query. Then it fans it out to all the search shards. And then each search shard does a search, scores the results, returns the results that they find to a blender or merger. They get merged together by score, and then the final set of results goes back to the searcher. I've left out some details out here, such as infrastructure that goes into the front end, infrastructure that goes into the browser, or infrastructure that goes into the device, your phone or your tablet, for example. A proper search stack has both infrastructure and relevance modules all the way to the device. And just to keep this picture simple, I've left most of it out. Within a search node, within a shard, you get a rewritten query, you have a retrieval module, you have a scoring module. They're separate from each other by design, so we can do the machine learning that I talked about. Documents are retrieved from the index that match the query. They're scored. They're stored in a heap, so we only want to maintain the top set of results that match the query. And once all the documents are retrieved, we return the top results. in the rewriter, what we have is a bunch of rewriter modules. Each rewriter module is focused on a specific function, for example, spell correction or query completion or synonyms or personalization and so on. These rewriter modules make use of data that is generally built offline. They're the data models you see in this picture, and they update a common state. And then at the end of the process, that state gets converted into the rewritten query that gets sent to the shards. Offline, this is what happens. We have a lot of unstructured data in Hadoop, the raw data. We can run MapReduces, and given that it's offline, given that it's big data, given that we have a lot of compute power, we can do a lot of stuff at this point. We convert the unstructured data into structured data of the kind that we want to put in the index. We enrich the data so that the amount of work we have to do online is minimized. We get derived data out of that. From there, we run one more final MapReduce step, which converts the structured data, the derived data, into a Lucene index and a bunch of data models for the rewriter. Okay, so what happens in the new stack? So we have a complete search engine. We have frequent reindexing possible. To rebuild the index, what we do is we go to Hadoop, we run all those MapReduces, and we get a brand new index. And once we have that brand new index, everything else that we did in the past is gone. That is history. We don't need that anymore. So it's a full reset of the world when we rebuild the index from Hadoop. Resharding becomes easy as a consequence. When you rebuild the index, specify the number of shards you want. If the index has grown, add a few shards if you want. It becomes trivial to reshard. And the other thing that we are focused is, that I didn't talk about yet, is we have tried very hard to make the infrastructure issues and the relevance issues nicely separated. So a relevance engineer should not have to worry about making an RPC or writing multi-threaded programs or worrying about capacity. How do I write relevance to handle 1 million queries a day or 1 billion queries a day or whatever? The infrastructure engineer's job is to do all of that and give a nice clean sandbox to the relevance engineer to just focus on what it takes to produce the best set of results for a particular query. All the scaling, all the computational complexity is dealt with by the infrastructure engineer. And we are focused on building a single stack, not a bunch of separate modules that are separately open source and so on. With a single identity maintained by a single team that works well together. All the engineers know pretty much most of the stack. People can work together better, and we want this to be a more stable way of moving forward that does not create the kind of fragmentation that we've seen in the past. Okay, some quick attributes. I'm soon running out of time. I need Kumaresh to come up and say something. Early termination is one very interesting feature of the new stack. What we do is we order documents in the index based on a static rank, from most important to least important. We define that by running some offline algorithm to assign a score to each of these documents. Then, benefit of doing this is that when you do the retrieval step, you could arbitrarily stop retrieving after a certain point. So suppose you have been asked for 10 documents, the top 10 scoring documents, and your retrieval query matches, say, 100,000 documents. You might be quite happy stopping after 1,000 documents, because our assumption is that the static score, that the static rank, is reasonably correlated with the score, with the final score that the scorer assigns the document. And with that assumption, we can make the search engine faster. A lot of people feel that this approach of early termination breaks down with personalized search, because maybe a result that is relevant to me might be lowest in the static rank. But in my experience, I've found that is not really the case, and static rank actually ends up working quite well, even for highly personalized search use cases. Okay, live updates. As I said, one of our very big problems is that Lucene forces us to update an entire document at a time. Lucene segments are document partition. Lucene has this concept of segments, so it takes the index and breaks it up into things called segments. Each segment contains a subset of the documents. But everything about a document is in a single segment. What we really want is term partition segments, and we've taken Lucene and extended it, enhanced it to have term partitioned segments. So what this means is that a single document, portions of that document can occur in different segments. All right? And you can modify a segment without impacting another. We use 3 segments. The first segment is called what we call the base index, which we build on Hadoop. It's the index that we build, let's say, once every week, and that never changes once it's built. Then we have this thing called the live update buffer, which is a segment that only sits in memory, and it gets updated with all the live updates that show up. Periodically, let's say every couple of hours, we take the live index, the live update buffer, and save it to disk into an index called the snapshot index. The snapshot index has already been built from a previous version of the live update buffer. It gets augmented with a new set of live data. So at all points, we have three different term sharded segments which jointly describe the documents. It's fault tolerant and performant. It's fault tolerant in the sense that you don't have to worry about your machines dying. You always have the base index to go back to. You always have the snapshots to go back to. You only probably have to replay the last couple of hours of live updates to get the live update buffer back to where it should be. So crashes are very easy to recover from. And then, big thing is no more content store. So when we have this, we don't need that second big storage, which is a full duplicate of the index. That's gone completely. Huge big savings, big relief out here. A little bit of a pictorial representation of these 3 different segments. We have the base index, we have the snapshot index, and the live update buffer. This is the same picture that I showed you earlier with horizontal lines describing documents, vertical lines describing posting lists, except that this is much denser. You have the base index with a lot of stuff, the snapshot index has a much fewer things, and the live update has even fewer. You can see that some horizontal lines cross all 3 segments, and the posting list traversal algorithms now just have to be expanded to be able to go through all these segments in parallel and do the right thing when there are clashes. Works really well. We only incur a slight performance overhead when you hit something in one of these other 2, snapshot index or live update buffer. For the large majority of cases, you will generally stay in the base index. Data distribution, when we have all these pieces of data, we have the base indices built in Hadoop, we have the snapshots built elsewhere. We need to get large pieces of data across to many different machines. We have lots of replicas of the search nodes of the shards being served, where we're serving traffic. We've built a BitTorrent-based framework to do that. I don't have time to describe it here, and we still need to clean that up before we can talk about it, so sometime soon. Relevance, we have a bunch of different places where we can plug in relevance modules. As I said, offline, where we do the heavy hitting computation, we do all the offline analysis. Maybe we can do spell correction there, we can do bigram analysis, we can do standardization of terms, unify computer scientists and software engineers, for example. Things of that kind that take a lot of time but add a lot of value can be done offline. Query rewriting. The purpose of query writing is to take a raw query and user metadata and convert it into a query that casts a reasonably wide net into the Lucene index to pull out documents, but not too wide a net that it pulls out garbage. So we just need to get an approximate bunch of matches from the index, and the query rewriting framework is plugged in through a proper interface to a Java, by implementing a Java interface in the infrastructure. Scoring, to fine tune each of the retrieved results. So you take that slightly wide net that you cast through rewriting and narrow down on the precise set of results to return to the user through scoring. After scoring, you do a couple of things. You do something called re-ranking, where you take all the results that the scorer returned and then further process it as a group. Sometimes you might have very closely related results. You might want to get rid of one of them. So deduplication, for example. Reorganizing the list to make related results appear close to each other. That's again a plugin at the broker level that again you have a Java interface that you implement. And finally, blending. So suppose you have a system where you have results coming from, say, a people search index and a company search index and a job search index, and you want to present them to the user in a certain order. That order depends on what the query is, what the user's intent is, and so on. There's a lot of additional ranking that you need to do to figure out what the order of these results needs to be like. I'm going to skip the next 3 slides. It's just a quick primer on machine learning, and it's a quick slide on how we do machine learning at LinkedIn. We have linear models. We have a tree based on query intent, and different query intents have different models. And given the shortage of of time, I'm going to not talk too much about it. If you have questions later, we can deal with it then. So what are the issues we have right now? So we've, as I said, we've done all this. We've launched a couple of verticals on it. We have a bunch of other verticals to launch. We need to now, we focus a lot on infrastructure, and we build some basic relevance support. There's a lot of richer relevance support that we can add, and we're working on that. For example, a spell correction loop might require multiple passes. You try to issue, you perform a search. If you don't get results, maybe there's a spelling error. You perform a more costly a spell corrected search. And there are various things of that kind that require more sophisticated relevance plugin capabilities. And we're working on that at this point. Scatter gather. Scatter gather is the process of sending results to a bunch of shards and getting results back. The biggest problem that anybody will have with the scatter gather framework is that if you have 10 shards, 9 of them will respond in a reasonable time, say 10 milliseconds, and this 10th guy will take 100 milliseconds to respond. There's always some uncertainty in the performance, and what happens is the performance of your search stack is always a function of the slowest node, search node. That's a big problem. We had to come up with ways of sending, waiting for a short period of time and then sending an alternate search request to a replica. This problem gets you inverse with Java garbage collection. You have 9 of them responding in 10 milliseconds. The 10th one is garbage collecting happening. It waits for hundreds of milliseconds. So that's a bigger problem, and we need to deal with issues of that kind. So we're working on some of these. And as I said, we need to extend the infrastructure beyond the backend. Search is no longer a backend problem. You need to think of search as a whole, as a holistic solution that goes all the way to the device or the browser. So we're working on that too. And finally, reintegrate all the diverging stacks back together. So as I said, we have search stacks, recommendation stacks, newsfeed stacks, ad stacks. As we build this new stack is capable of handling the scaling needs of all these other infrastructures. Bring them all back together and get the benefits of the integration in a single stack. So this ends my presentation. Now I'm going to get Kumaresh to take over from me. We'll talk about the product details.
Thank you, Sriram. Thank you all for being here. It's, as Ravi mentioned, I used to work at Microsoft up in Seattle, and I wish I had known how nice it is out here. So I'm going to be talking about how the infrastructure that Sriram described helps us build search products at LinkedIn that are core to the LinkedIn member experience and to its business. So I hope to give you a product overview that talks about how how members on LinkedIn use search, who are these members, and why it's important to LinkedIn. So it all starts with LinkedIn's vision. The vision to create economic opportunity for every member of the global workforce. Put simply, that means to help everyone that's unemployed find a job, and everyone that has a job but is uninspired at work to find their dream jobs. And for those that are already in their dream jobs, be insanely great at what they do. And what that means is for them to be giving back to the community, for them to share their insights about being great, and to help others find their dream jobs and be great at what they do. In order to realize this vision, we aim to build the world's first economic graph. What that means is that we want to digitally map the global economy. We want to have a digital representation of every member of the global workforce in the form of their profile. We want to digitally represent every company, every job, every skill that's needed for those jobs, and every educational institution that gives us tools to build these skills. We want to be able to overlay professional knowledge that empowers all of these entities in the economic graph. And search happens to be a core part of this economic graph vision. Because if you're talking about a billion node graph with all of these entities in it, with all of these complex connections between these entities, like the connection between you as a professional and your university, the company that you work at, and the skills that you have. It's going to be a challenge to traverse a billion node graph without search. Today, LinkedIn search lets you power, it powers people search, jobs, groups, universities, companies, and influencer content. And so it has set LinkedIn on its path of building out this economic graph. So let's discuss a little bit about who uses search. It starts with the casual user, the average LinkedIn member that uses LinkedIn on a monthly or a weekly basis. They think of LinkedIn as their professional identity, and they don't necessarily actively network on LinkedIn. Then comes the outbound professional, the recruiter that's looking to hire talent, or the sales professional that's trying to gather sales leads and prospects. They think of LinkedIn as part of their day job. There's a tweet that might be hard to read here that says, "Dear LinkedIn, your search is down. What am I supposed to do at work today?" It's one of those bittersweet moments for a product manager, in that your product is down, but at the very least, you have someone noticing. This was interesting in that the product actually went down for an hour, and there were quite a few recruiters, quite a few sales professionals that were complaining about spending $8,000 for a seat and not being able to do their day job. It means that much to them. Next up is the job seeker, who thinks of LinkedIn as a way to get this day job. So let's walk through a few use cases of how these users use search. So it starts with the casual user who predominantly does name searching. They want to find someone on LinkedIn by name. The product that lets us do that is Instant. It's something we launched in the past month, and it's the first use case that's powered by the infrastructure that Sriram was referring to. We have a code name for it, and we'll be launching it in a few weeks from now. It lets you search all members on LinkedIn by name or approximate name instantly. So in this case, I'm able to find Deepak Agarwal by, despite mistyping the first name and the last name and not having typed the entire last name. This is one of the most common use cases in LinkedIn, in that 60% of search on LinkedIn is navigational in nature. You have one entity that you want to navigate to, and you want to do that instantly. Another thing the casual user does is topic search. We have one unified search results page that brings together entities that we have to offer that are relevant to a given topic. Take Spotify as one of the examples, where we have the company page for Spotify and people who work at Spotify and jobs at Spotify in one unified search experience. We try to cater to all of the intents that a searcher could be having as they want to research more about this topic. As with this other example on career advice, where we have influencer posts offering career advice, along with people who can offer you career advice. So that's the casual user, the average LinkedIn member. But when we talk about building a product that also caters to our advanced users, our power users, it brings us to outbound professionals. They're primarily on LinkedIn to explore people, to search for people. And the way we build products that tailor the exact same products to be used by a casual user as well as an outbound professional is by, for instance, having search suggestions in Instant, where when you're typing in a company name, which in this case is Bloomberg, we are able to identify the fact that you are referring to the company entity, and we are able to surface suggestions that will let you explore people at Bloomberg, such as people who work currently at Bloomberg or people who used to work at Bloomberg. We are able to enable discovery of these capabilities right in the instant surface as you type. a similar use case with skills, where when you type in Java, we are able to expose the capability to look for people that know Java. As you can see, we are expanding out this glossary, starting with companies to skills, titles, locations, and all keywords that we typically see as part of exploration with people search. In fact, all it takes is one keystroke for you to go from name search to exploratory search. In this case, you start off with filler, which is a very likely first name. We show you instant results for filler. In this case, there are 8 people with first name Philip. You type in a S, and suddenly Philips is a company entity. We want to offer you people who work at Philips, along with the company page, and people whose names have Phillips in them, like Christina Phillips in this case. Notice also how Phillips is spelled with 2 L's, and we are able to do that instantly. We are able to match approximate names. And so that's how instant is tailored to cater to both the average user as well as the power user. Once you issue your query, you're on the people search page. We have this page tailored for exploration. What we have is facets and advanced search fields that will let you explore people more effectively. We have facets for people at a given location, at a certain company, with a certain title, that went to some school, even people that have a certain level of seniority. This is the product that hopefully the woman in the IBM video is looking for. The search results present the network, the power of the network, in that in addition to presenting your degree distance to a certain member, we provide you we provide you ways through which you can reach out to that member. So in this case, Justin is a second degree connection of mine that I can reach out to through Daniel. And that's present as part of how we present the search result. In addition to building out a LinkedIn.com experience for search, we have standalone products that are tailored to the recruiter and the sales professional. And these products have search as the front and center of their experience. You can see how the mobile recruiter app presents results in such a way that you can swipe across profiles to explore a whole bunch of designers with minimal effort. Likewise,